Welcome to this webinar. This webinar is for your final project for the nano degree. The project is for collaboration and competition. In the previous project that was on continuous control, you used one DDPG agent, that is the deterministic policy gradient agent. So for this project, you have to use multiple of those DDPG agents. So today I will go over the project details, the key points of the project, what are the requirements for submitting this project, and then I will go over a quick overview of the multi-agent DDPG uh, process, how you can implement it. Also, if you check this introduction to multi-agent RL lesson, there are lessons and there is a lab which also implements this multi-agent DDPG. Also, there is this paper by OpenAI on multi-agent actor predict for mixed cooperative competitive environment. So you can read this paper to get an idea of different situations where multi-agent DDPG can be used and how it can be implemented. So you can get your ideas from this paper as well as the lab, and also what I'm going to explain today, the general process, how you can implement it. So it's up to you which approach to use, um, and uh, and I hope you can successfully submit this project. So let's go over the details of the project. All right. So basically, this environment originally is from Unity ML, but Udacity has provided an identical environment to this. So it's not the actual environment from Unity's GitHub page, but Udacity has created another environment which is similar to that. So please go ahead and read this. Some good information here, and yeah, it says that for game developers, even multiple agents can be used to develop game, to test games. You might have heard about DOTA, the Dota agent created by, I think it's by OpenAI, which solves the DOTA game, Dota game. It's on YouTube. You can look over. You can check that video. Also, so let's get into the environment. Okay. So for this project, you will have to solve this tennis environment over here. So basically, there are two agents, and they have to avoid this ball from hitting on the ground, or they have to avoid this ball from getting out of bounds. So two agents control rackets to bounce the ball over the net, and if an agent hits the ball over the net, it receives a reward of plus zero point 0.1. And if an agent lets the ball hit the ground, its own ground, okay, or hits the ball out of bounds, then it gets minus 0.01. So based on this reward, you should know what the motive of this motive of solving this environment is. It is not to defeat your opponent. Okay, it is to defend yourself from to avoid the ball from falling in your area, or to avoid the ball from going out of bounds. It is not to defeat your opponent, or this agent is not going to try to hit this ball to the ground. Okay, based on the reward, the each agent will just try to defend uh, its own turf. So it's so if you see if you see a trained agent, and if you apply it to the environment, if you make it play, you will see that both agents are just bouncing the tennis ball back and forth. You'll see a continuous uh, loop of the tennis ball going from one agent to another. You won't see an agent trying to beat another agent, uh, because that's how the rewards are described here. Okay, they have to hit the ball over the net. They get plus point one. So they have to avoid hitting here, and they have to avoid the ball hitting their ground or throwing it out of bounds. Okay, so it's not the reward is not to defeat your opponent; it's to save yourself from the ball falling on your turf on your side of the court. And then there is a description of the state space, 8 variables, uh, and then there is action space, uh, two continuous action space. So state space is continuous, action space is also continuous. So this should give you an idea of which output functions to use, and what will be the input layer, and what will be the output layer size. Okay, now it says 8 variables, but you should check out what is the size of the state space for each agent. It could be different than 8. Okay, so you can check the size of the observation space. Task is episodic. Okay, and to solve the environment, agent must get an average score of plus point 0.5 over, as usual, previous 100 consecutive episodes, and you take max over both agents. So there is more description about it. So you add up the reward for each agent during an episode, don't discount it, and you take the max score of both the agents, and that is the score for that episode. Yeah, and so that is the core score of one single episode, which will be max of the score of both agents, and then you average previous 100 scores, last 100 scores of the last 100 episodes. So this is important how you um, compute your score and how you take the mean. Well, more important is how to get the score. You have to use the max function. All right, and plus 0.5 is when you solve the environment. You can also go beyond plus 0.5. Plus 0.5 solves the environment, but that doesn't make it the best score. Obviously, you can keep solving it, and you can make it better and better, and get as higher score as possible. Okay, the higher the score, the better. Well, it depends on your plot of the scores. It should be a stable score. Okay, I'll discuss that more later. Okay, the environment. So there are instructions so how to download the environment and how to get it running. So as usual, you have to download your OS version of the environment. Place the exe file in your workspace directory. Uh, right, and all these instructions about AWS. You can explore the environment. You can see this if it's, yeah, it shows you how you can place all these things, shows you the state space. Yeah, so okay, hold on. You can see here the state space. So number of agents is 2, size of each action is 2. So for one agent there are 2 actions. So total size of the action array will be 2 by 2. Okay, there are 2 agents. Each observes a state with length 24. So the total states, the states shape of the state array will be 2 by 24. So one row each for each agent. Similarly for actions, one row each for each agent's action. So 1 by 2, that's 2 by 2. This is going to be 2 by 24. This is just for one agent. Okay. And you can also print out uh, other things like rewards, how what is the shape of the reward variable, and etc. to get a better idea of what's going to happen. Yeah, and this is an example of an untrained agent. Yeah, because it's just letting the ball fall. 0 0 0 score. Okay. Optional, build your own environment. You can do this later once you have solved this. It will take some time because you will have to download the Unity application, and there are some tutorials you can follow. If you are really interested in game developing, you should try this, because if you suppose you are developing your own game and then you want to test it using using a trained agent, then you can build an environment which is a replica of your game, and then you can do all these things. Okay, project instructions. So this is the instructions on how to submit the project. Project rubric is here. You have seen this many times. Again, there has to be a readme file, code, and a report for GitHub repository. And I'm sure most people submit GitHub only, not zip files. And so what the readme should have, okay, let me show you a sample of how should look like. So this is how the should look like. So, a description, like, so if there's a newbie who doesn't know anything about DeepRL or even this project, they should be able to find their way from this README file. So I've included the paper on what this is based, a paper to help them solve or understand what's happening. Then this is optional. It's up to you if you want to show a sample agent. This is a trained agent, and you can see they are not trying to defeat each other. They're just trying to hit the ball over the net and save their own ground. That's it. And then you can include the information about the environment, all those things we just discussed. Then how to download and get this environment running, and then a brief description of your algorithm and what files you have included, and some conclusion, and then some resources if you want to show. So readme should describe how someone not familiar with this project should use your repository. It should be for a general audience, and how to install and all those. Describe your environment that you solved, how to install the requirements, everything. Okay, then the code should have all the training files, all the Jupyter notebooks or the Python scripts that you used to train the agents, as well as the trained model weights, your best model weights. And there should be a report file. It could be report.markdown or report.pdf, and you have to describe your algorithm, how the process works and everything, so you can check here. So yeah, and then there is instructions about the workspace. Use GPU only when you want to train your model. Don't use it when you are writing your code, or if there is any syntax error, any errors. First figure out all the errors, clear all the errors, and then you use your GPU. As always, you know all these things. Okay. Benchmark implementation. There is a sample, some hints given here. So yeah, uh, too many hints for this project. Start with DDPG code to solve this project. Yeah, so you can start with DDPG. You can make a multi-agent DDPG uh, algorithm, and then maybe you can build upon it. You can use something else other than DDPG. Start with basics and then make it more and more sophisticated. Okay. Yeah. So again, this is not acceptable that you might solve the environment. So it crosses zero point 0.5 here and even goes to 1 around, but then it falls. So this is not acceptable. It should be a stable agent. Okay. So please take a note of that. Yeah, you can share and ask people. There is this workspace. This is for me, but ignore this. This will give you the basic basic notebook about this environment. And once you have solved this environment, and if you want to get your hands dirty, you can solve this more difficult soccer environment. So in tennis, there is only one agent each on both sides. Now there are two agents on each team, and here you can download the soccer environment and everything. So you do try this after you have solved the tennis environment. It's good for your learning. And then in the end you submit the project. Yeah, same description. This is the project rubric, how you will be evaluated, and you submit here. Okay. uh, you should do read. I suggest you read also the paper, as I've already said. But yeah, it's there is a good information. Now the paper doesn't have exactly same environment. It has these these multiple agents, and there is a they're trying to reach X. Yeah, so this is what is solved uh, in our lessons. There are two agents. There is one adversary, and they are trying to reach an X, and they are avoiding another X. Very interesting. You should check this out. We have already provided the code for this. Check that out. And not just this, but in this paper there are other environments, and you can take hints from them to solve your project environment, and even many other environments you might want to solve. So there is information in this paper. Very interesting. uh, yeah, and very informative. Okay. So so let's go over. I'll explain to you like basic workflow of the multi-agent DDPG algorithm that you can follow. You might get some ideas from it. So let's see here. Okay. So I guess today's webinar is going to be very short one, but yeah, let's go ahead. So multi-agent DDPG overview. So you have seen this flow, this algorithm in our DDPG webinar. Uh, and basically it's, this is just one agent. So state, environment gives a state, you get action, then you put this action to the environment and it returns a reward and next state, right? And you input the next state to your actor target, right? So there are two actors and two critics here. So you input next state to your actor target, it gives out next action, okay, given next state, and then you use these two to compute your action value, this should be q, so action value for next state, which you can use to compute this TD target, right? By now you should know the equation for TD target, and then you use this action and state, input it to your critic local, compute state, sorry, action value given state S and action A. So there will be two inputs here. There should be an A here. Uh, and this should be Q. Sorry about this. So this is the action value given state S and action A. And then you train this in order to reduce the loss between this and the TD target. Once you have trained this, you you yeah, so once you have trained this, you again get a new action based on the most recent version of your actor network, and then compute another queue, this queue, using this S and the most recent A, and then you train this network in order to maximize this queue. So that means you have to minimize the negative of this. And I said, and we have also discussed this in the DDPG paper, sorry, DDPG webinar already. I said most recent version, right? So that, why I said that, because when initially in the beginning, when you input S and get action A, this state and action, okay, you get these two, and then you use this action, input it to the environment, and it gives you S prime and R, and then you add this to the replay buffer, and when you train, they are sampled from the replay buffer. So uh, this S prime won't be, this S prime is sampled from the replay buffer, and similarly this S and A, sorry, this S that goes into critic local is also sampled from the replay buffer. That's why you need to get a new action, get a new sorry, this set and A will have sampled from the replay buffer to first train your critic local. So in order to train this, to maximize this, you need to generate a fresh action based on your most recent network. Since you are sampling this, it might not be based on your most recent version of the network. You are sampling this for computing your and critic target, and then training and so on. Okay. So this will be more clear when I go to the multi-agent DDPG network. So this is just one agent. So for multi-agent, there will be two agents. There will be an algorithm, let's call it a parent agent, and it will have two agents. So this agent one will belong to, if you based on your environment, this will belong to my blue racket, and so this will control my blue racket, and this will control red racket, red racket. Okay, and each of these agents will have these four networks, all right, that we saw previously. But the training is slightly different because we have two agents. So let's see that. And don't worry about this. Just I said about the sampling and all. It will be more clear when I show you the further stuff. Next slides. Okay. So there is a parent, and it has two agents. So I will create a parent class, and I will initiate two agents in it, and each agent will have four networks, two of which are actor networks, actor local, actor target, and two are critic local, critic target, and same for agent 2. And you have to train these two, actor local, critic local for agent 1, and actor local, critic local for agent 2. Okay, so let's see how we do that. Okay, so as we saw in the description, the environment gives out state in this format, in this dimension. So that's 2 by 24. So 1 by 24 for each agent. So this is the basic state generated by the environment. When you use environment.reset, the initial random state that's generated by the environment. And it's important to remember that this is 2 by 24. You haven't experienced this before in previous projects. All the previous projects had only one state, and it belonged to only one agent. This time, there are two rows, uh, and each of those rows belong to one agent each. Okay, so 2 by 24, you have to take the top row and use that as state 1 for agent 1, and the bottom row for agent 2. Okay, so what happens with this? So S1, let's call the top row that you got, and it belongs to agent 1 as S1, and the state that belongs to agent 2 as S2. So with S1, I input this to the actor local network of agent 1. Okay, and I get action with dimension 1 by 2. Okay, similarly, I input the bottom row from here, 1 by 24, to actor local of agent 2, and then I get action which is also of dimension 1 by 2. Okay, now I take this action and this action together, I stack them top of each other, and I get action of shape 2 by 2. Okay, and remember that the order should be the same. So if the top row was agent 1, bottom was agent 2, so when you put together this action, A1 should be top, A2 should be bottom when you stack them. So the total action space is 2 by 2. I input it to the environment. Remember the environment.step uh, command. So action will go into the environment, and environment will give me next state, which is also 2 by 24, just like this. Okay. Now again, the top row belongs to agent 1 of the next state. Uh, Upper row of the next state belongs to agent 1, and second row of the next state belongs to agent 2. Now how do I use this? So I take, and I will call the top row of the next state as nx1, ns1, that's next state for agent 1. So I input this again in the actor target network of agent 1, and I get next action 1 from the actor target. So this was actor local, this is actor target, and I input the lower row from here and call it next state 2. Okay, input it to actor target of agent 2, and I get NA2. Okay, now I'm going to stack these together and call them as next actions here. So once I've done this, uh, after this step I'll get next state, but I will also get reward and duns from the environment. We have seen this many times. So I will make a tuple of states, so S1 and S2 stack together. Next state, so NS1 NS2 together, so both are 2 by 2 4, 2 by 2 4, 2 by 24. Then actions 2 by 2 from here, next actions 2 by 2 from here, from these two, and then the rewards and turns that the environment gives me. So I will stack them and I will make a tuple, and I will add to buffer, and I will wait until my buffer has enough experiences, so that I can start sampling from it. Okay, as usual, we have seen this so many times. Next, so what happens next? Now we start training, And now the process that I'm going to discuss is only for agent 1. But I write loop here because we have to loop it. So you do uh, for I in 2, so in range 2, and then you do the whole training process for agent 1, and then you do the whole process for agent 2. That's going to be the loop. What's the first loop for just agent 1? And you have to repeat the same actions for agent 2 as well. So for agent 1, first of all we sample from buffer. So once, depending on your batch size, uh, you sample these tuples. So, and we call this as experiences, if you remember from your code: states, next state, action, next action, rewards, and done. And remember that since we have sampled these from the buffer, these might not be the same that we got here, right? We are just randomly sampling from a buffer. Okay, but they belong to each other, right? So the states, next states, actions, and next actions, they all belong to one tuple of SA, R, S prime, A prime, right? But they are all stacked, right? So we and you know all this already from DQN and continuous control and navigation project. Okay, so we sample these. Let's say they are, let's say your batch size is 128. You have a batch size of 128, let's say. Okay. Then what I do is I take the next state uh, of agent 1. So from in next states will be 2 by 2 4, right? It will be 2 by 2 4, and since it's 128, it's going to be 128 by 2 by 24, right? But I will only discuss for the very first experience. Okay, so it's 2 by 2 4. So 1 by 2, sorry, 1 by 2 24, 1 by 24 for each agent, as we previously saw. So n state 1 is the 1 by 24 for agent 1. So that's the top layer. Next state 2 is from next state, the bottom layer, again 1 by 24. Next action 1 is again from here. Okay, again I have written it sampled. These are all sampled. These are not the same that we saw in the previous step. Okay, these are not from the collection step. These are from the sampling step. So next actions A1, top layer of this. Next action A2, bottom layer of this next action. Okay, you have to stack them all together and input to the critic target network of agent 1. So if you can see the similarity now between this process and the process of the very basic uh, DDPG agent, the critic target here, we used to put next state and next action of only one agent in the critic target and compute the queue here, right? The action value. But since we have two agents now, we have to stack up next state of both and next actions of both. Okay, so we start with the next first, not the current. Okay, so we compute, we stack them together, pass it through, input it to the critic target network of agent 1. Okay, that will give us a queue action value for agent 1. Okay, I will use this to compute the TD target. Now you should know what the equation of TD target is. You have to use the rewards and the discounting factor times this. I will leave it to you. So you got the TD target. You computed this. Then I will take the critic local network of agent 1, and I will input the sampled S1, S2, A1, A2 from here. State 1, state 2 from here, A1, A2 from here. I will input it to the critic local. So this is critic target, this is critic local, both for agent 1. I will input this. I will get Q current agent 1. Okay. Now I will train this network in order to minimize the mean square error loss between TD target and this value I have generated here. So the motive is to make the parameters here such that this and this become as close as possible. Okay, so you have updated this. You have updated your critic local agent 1. So that's half of the objective of our process for agent 1. Now we need to train the parameters of actor local for agent 1. Okay, and this is only for the loop for agent 1 currently. You will do the same thing for agent 2 as well. So we have this updated network. Now you have to first get the most recent version of your actor local agent, and you have to input the sampled state to the actor local agent and generate new action here, new A1, which is of 1 by 2 shape. Okay, so this state is sampled. It's from the buffer and the batch size, that 128 batch size. But this state is from here, top row S1, and I sampled it, and this is from the sampled one. Okay, I didn't resample it. This is the same sampled uh, batch, and I take the state 1 from the states. Okay, and I input it to again. I input it again to actor local network of agent 1, and I get new action. So I'm not using the sampled action here. I'm generating new action here. Okay, same thing with actor local for agent 2. I use the most recent version. I'm saying most recent version, but I mean that run this sample state again through the actor local network of both the agent 1 to get new A1 and agent 2 to get new A2. Okay, so that's the difference here. New A1 is different from the sampled A1 from the sampled A1 from the actions, and new A2 is different from the A2 from again this action. But I do use the sample states. So what the motive here is that, okay, previously I had this state and I got this action during some previous version of the network, but I need to see what the current version of my network is doing, how it is performing, so that I can figure out how much to train this parameter, so how well to train, because you are going to train the most recent version of your networks, right? So that's why I input the same state, but I get new action. So I get an idea of how my current version of my local network is doing. Okay, I got this as well. Then I take sampled S1 and S2 and new A1 and A2, stack them together, make a flat array, input it to critic local agent, the updated version. This one we just updated this by running back propagation here, right? We updated this, and so here I'm saying is, okay, now I have a new critic local. So let's see how my new critic local performs given the same states but new actions. So this is what you get. So this makes it more relevant, right? If you had used same A1 A2, then uh, you would be wrong, because you won't you won't get the correct picture. What's the actual value of your action value is given these states and actions. So first you train your critic local network, and then you use sample states but new actions from the most recent version of your actor local networks, and you get Q new agent 1. Okay, since it's critic local for agent 1, I call it Q new agent 1. Then I will update the parameters of my actor local network. Okay, the most recent, the current version of it. And I don't have to mention current version, because when you initiate your optimizer, you say that the parameters are going to be actor local dot parameters, right? If you have written the code yourself in the last two projects, you should understand this. And then I run the same backpropagation step by maximizing Q new agent 1 that I got here. And you should understand how to maximize this. Backpropagation usually minimizes things, but you should know how to maximize, right? So that's how I trained my actor local for agent 1. So this is a loop just for agent 1 where I trained my critic local network for agent 1, and then I trained my actor local network for agent 1. Then I do the same thing for agent 2's network, and I will train critic local for agent 2 and actor local for agent 2. Same process. So this is uh, I can't show you the actual code, but this should give you some idea of how to approach this project. And it's up to you how to organize these networks. There are modularized version. There was an example of how modularization can help or make your code more efficient. You can do that as well. You can, because we are using so many instances of same kind of network. So you can modularize things. It will make your code cleaner. um, yeah, so it's up to you how to organize all those things. And you have to select your randomization parameters like epsilon, your hyperparameters, uh, um, the OU noise function, what parameters to use there, your batch size, your uh, right, how often you want to train both agents, and you should train both agents um, during each training step. So if you are training agent 1, you should go ahead and train agent 2 as well at the same time, back to back. Okay, don't just train one agent and leave the second one for later step. uh, I advise you don't do you train both back to back. That's why I included loop here. And yeah, so that's all. That's all. That's a pretty that's a lot of information for you, and a lot of information is also available in the paper. And this, yeah, the multi-agent paper was discussed here, so read that paper. It's very interesting paper. um, and that's it. If you have any questions, queries about the final project, and it's a bit complicated, it's not difficult to implement, but you should organize your networks well and modularize as much as possible. That's my suggestion. If you have any problems, please feel free to reach out to me on Slack, and I will get back to you uh, as soon as possible. So yeah, so I will end the webinar now. Thanks for watching this.